Okay, good afternoon, everyone. Thank you for joining us on our call today. My name is Nicole Van Wert Quincy from Transcat, and I'll be your moderator this afternoon. Our webinar topic is how to calibrate sanitary temperature sensors and transmitters. It's being presented by Michael Coleman from Fluke Calibration. Michael has been with Fluke Calibration, which is formerly Hart Scientific, for 19 years. He has worked both in the temperature calibration service department and in the primary temperature calibration lab. We expect today's presentation to last roughly 30-35 minutes, and then we'll answer any questions that have been submitted during the presentation. During any time, you can submit the questions through the question box to the right in your webinar controls. I also wanted to mention that the webinar is being recorded. You will each receive a follow-up email with a link to the recorded webinar and the slides of today's presentation later this week. At this time, I'm going to turn the presentation over to Michael.
Thank you, Nicole, and thank you everyone for attending. As Nicole said, today we are here to talk about how to calibrate sanitary temperature sensors and talk about what they are. And the discussion will focus a lot on a fairly new Fluke product, the model 6109A and 7109A portable calibration baths that were designed for this application. And as Nicole said, my name is Michael Coleman. I work at Fluke Calibration in the temperature calibration department, and I work and am presenting the webinar from here in American Fork, Utah. And I've worked in calibration now for about 19 years, and have really enjoyed it. It's been a great career. So with that said, we'll jump right in here. Sanitary temperature sensors are used in a lot of process manufacturing industries. They are very common in the pharmaceutical and biotech clean room facilities, and they come in a variety of shapes and sizes. We have a few examples here of different tri-clamp sensors, and some of the challenges with them for calibration professionals are the odd shapes and sizes, and especially sometimes it can be a real challenge is the large transmitter head that's attached on the tri-clamp sensor. So let's talk about why we call these tri-clamp sensors. Tri-clamp refers to the mechanical housing of the temperature sensor, so the temperature sensor can be installed easily into a tri-clamp system. And we'll have some more pictures coming up here to show you. The tri-clamp sensor is typically made out of stainless steel, or the entire assembly is made out of stainless steel. And the flanges that you can see vary in size from a 1/2 inch to 3 inch diameter. And again, the flange is on there to make it easy and efficient to install these in a manufacturing or a food production process. So here are the pictures of the actual clamping system. You can see in the picture on the left, there's a clamp that goes around the flange, and the flange mates up with the piping system that's in the facility, and again makes it easy for someone to take the sensor out and calibrate it. And you can see on the right-hand picture where the temperature sensor now is inside the in this case a T fitting that would be in the plumbing or the piping system, and so that the temperature of the material going through there can be measured, and then that measurement sent off to either a B or a 4 to 20 milliamp control system in the facility. So some important factors to consider when calibrating sanitary sensors or tri-clamp sensors is, first of all, consider the temperature source. And what we mean by temperature source is the tool that will provide the temperature set point needed for the calibration. And probably the main specification to consider is the overall accuracy of that device. Many of these temperature sources, like these baths or dry block calibrators, have a built-in display with an accuracy specification that hopefully covers all of the pertinent sources of error or sources of uncertainty, like stability, uniformity, repeatability, so that you as a user can it makes your job a lot easier so that you can use this comprehensive specification to know what to expect and to build up your to make sure you're using equipment that's adequate for the application. Some other things to consider are things like immersion depth. One of the largest sources of error for a temperature measurement can be immersion effect, or error caused by the sensor not being sufficiently immersed into the measurement medium. And so having a proper amount of measurement depth can help remove these errors. And again, with tri-clamp or sanitary sensors, this can be a big challenge, because some of these, as you saw in some of the pictures, might only be 2 inches long, and with a lot of mass, a lot of metal mass surrounding the temperature sensor. So we'll talk about that a bit more here over the next few slides. Calibration throughput is another concern. In many applications, there's benefit with calibrating more than one sensor at a time. So that helps reduce downtime in the process where the calibration is being performed, and improves productivity overall. And factory managers typically really enjoy that. And then finally, the last thing is we'll be talking about a bit more is calibration traceability. A lot of industry requirements specify calibration traceability, but sometimes the way the measurements get broken down, we see gaps where sometimes there isn't complete measurement traceability. And so we want to make sure we share some thoughts with you on that, to make sure that in your facility you are covering measurement traceability appropriately with these sensors. For example, one reason why this can be an issue is because in some applications the technicians are only calibrating the transmitter, and they consider the sensor that doesn't need to be calibrated, or the sensor is some kind of intrinsic standard that doesn't need recalibration. But the reality is the sensor drift alone can cause as much as 70% of the error budget, or the specification for the transmitter and temperature probe system. So first, we're going to talk about temperature sources a little more specifically, what the different types are that we typically see being used. And so first, a very common type is the dry block calibrator. So this is often referred to as a furnace, or a calibration furnace, or a dry well. And these are they're called dry block calibrators because typically they don't use any fluids. There's just a metal block with holes machined into the block that will accommodate temperature probes that can be put inside inserted into the block or the insert. Sometimes there are some hybrids where they are dry block calibrators, but they will have a small well filled with fluid so that a temperature sensor can be put into. But usually these are the inserts or the blocks are fairly small dimensionally, so they can only accommodate one sensor at a time, just because of the size of the transmitter head, or the size of the flange on the tri-clamp sensor. Circulating baths are also sometimes used. Sometimes we'll even see folks taking a calibration bath that's designed to stay in a cal lab and rolling it around a factory, because they really appreciate the larger tank size and the ability to put sensors of all different sizes and shapes down into the fluid to get a better calibration. But these larger baths are again designed typically for the cal lab, and they may take a long time to change in temperature. They have very, very good stability and uniformity specs, but aren't really ideal for use out in a factory setting or out in the field. And so then Fluke has a line of calibration baths that kind of help cover the best of both worlds here, where they are smaller and portable. We have two general categories. One is a product line that's been around for quite a while, the 6102, 7102, 7103 micro baths. We see these used all over the place. They're very popular. The display accuracy is around 0.25 degrees, so they can accommodate a lot of industrial calibration processes, but the tanks are fairly small, and we looked at those and realized that there are some good design improvements that we could incorporate. And so we came up with a newer model line, the 6109A, 7109A Portable Calibration Baths. And they were designed specifically to accommodate sanitary sensors, but they are also, in general, a calibration bath that can solve a lot of the problems we've been talking about. So here are some pictures of these baths, and we'll go into a little more detail on some of their features. And then in the end, if you have more questions about specs and whatnot, we won't be going into the specs in detail in the webinar. We're just introducing these baths and some of their features. But we're happy to answer any questions you might have spec-wise. The reason why we're saying that they can calibrate 4 times more throughput than other macro baths or the micro bath line is because the tank size will accommodate 4 time. And you can see a picture there of the 4 sensors installed in there with a reference thermometer placed in the center of the bath. The temperature range for the 6109A is 35 to 250, and then 7109A from -25 to 140. And the accuracy of the temperature displayed on the instrument is 0.1 degrees C. And this, as with other Fluke products, takes into consideration long-term drift, stability, calibration uncertainty, and everything. So it's a comprehensive specification that covers these sources of error or sources of uncertainty. It's designed with stainless steel, so it can be used in a clean room and be easily cleaned, and with some of the chemicals that are required for cleaning clean room instruments. And because it's stainless steel, it won't harbor bacteria, which was a big deal for the customers that we worked with on developing this. So it's portable. You can see the handle there on top, a nice strong handle, so you can take it into facilities where you need something that's portable. So these tri-clamp sensors that we're showing have 2-inch flanges, I believe, if I remember correctly. And what we I need to back up a little bit. So what we want to talk about really quickly here is the importance of immersion depth. We kind of mentioned this earlier, and so these sensors are often just like the one shown here, where they have short sensors because they have to plug into a pipe, and then they'll have a flange. And so we wanted to make sure that the tank was big enough that the entire assembly could be lowered down into the fluid, so that you're not getting heat loss or stem effect because of the flange being at room temperature and the temperature sensor down inside the bath. And so we recommend that, if possible, if the sensor is long enough, that it is immersed until it's about just a little over a ½ inch above the bottom of the tank. But not all sensors are long enough to do that. And we recommend that minimally the sensor is immersed so that the flange is down inside the fluid, just to help prevent heat loss. If the sensor happens to be much longer, like 6 inches in length, the sensor sheath, then it's probably not necessary. Well, actually, I should say it's not possible to put the flange down into the bath fluid. But for shorter sensors, it's recommended to allow the flange to go right into the fluid, as shown here in these pictures. So what we want to talk about is a couple of different calibration methods that are possible using this type of calibration system. The first method is where the sensor is removed from the pipe system in the factory or the facility, and the sensor, along with the transmitter, the assembly is kept together. Is the sensor is put into a bath, and then the transmitter and temperature sensor are calibrated as a system by comparing the bath temperature display with the control room display or the controller if there's a local controller connected to the temperature sensor. And we'll go through that in a little more detail. And I need to talk about the advantages and disadvantages. The advantage of this type of calibration is that you are doing a loop calibration or a system calibration where the transmitter and probe get calibrated together. It's a kind of a one-step calibration process. This is a little bit faster because you don't have to worry about disconnecting the sensor from the transmitter, and it does maintain full traceability. The transmitter and probe are calibrated as a system, so the traceability is fully intact. The only disadvantage is that sometimes there might be an issue with the transmitter or the sensor that might not be detected calibrating it as a system. And so the other system helps take care of that, or sorry, the other method we have here helps take care of that by disconnecting the sensor from the transmitter. And now we have a calibration scenario where the transmitter is calibrated with its own calibration, and then the temperature sensor is calibrated in its own calibration. The advantages here is that we now are able to look at both components in this calibration process. We also still maintain full traceability. The disadvantage is that it's a little bit slower to do this because it's two separate cals, and also you have to take the time to disconnect these components from the system, the controller system. And there's also no system verification. Now, we anticipate in this method that once the two components are calibrated, when they come back together, everything will work correctly. But I know some facilities always want to have a little extra warm fuzzy on that to know that the system, that the two components working together is working correctly as the theory dictates. So in this example, we'll be using a 7109A bath that goes from -25 to 140, and we've just selected some temperature points to be an example of what you could do. So 0, 70, and 140. So the first step is to take the tri-clamp sensors out of the tri-clamp system and place them into the bath. You can place them into this probe holder fixture to help hold them up while you get them all set up, and then use it to the sensors. Then step 2 is going into the 7109A display and set up a calibration program. And in the calibration program mode, you can program it to run through the temperature set points that you want to use have it do this automatically. And it also allows you to insert dwell time for each set point to make sure if you need some extra, you can specify the time you need to make sure you get the stability and uniformity that you need for your process. Then after that, you can start running the program, and it will start at the first temperature point programmed in, which is 0 degrees C, and the bath will show the temperature set point it's on currently, the actual temperature inside the tank, and then also how much cooling or heating is being required to ramp up or maintain the temperature. We don't have there is a picture here. I was just about to say, there's also a light on top of just above the controller that's called the ready indicator, and when the bath sees that it's at sufficient stability, it will turn on this light to let the operator know that they can go ahead and take measurements. As the program is running, you can use the monitor button and pull up a graph if you want to see what the temperature is looking like inside the tank. So then step 4, when the bath is at the set point, this is where you take the data and you will have to look at the controller display and compare that with the display on the 7109A. And sometimes the control display may be off in a control room, and you may have to have a second person help you out with that, and so you can take that data. And then you just continue these steps through the other temperature points. All right, so the second method, this one's a little more complicated, and we're bringing in another piece of equipment in case there are more sensors that need to be calibrated. The 7109A has if you have the P-board option, which I guess we should have shown a picture of one with the P-board option. Oh, we'll have a picture coming up here soon. Anyway, the process electronics option will accommodate measuring one DUT sensor, but if you have multiple DUT sensors, because the tank holds 4, then you will have to bring in a readout that will measure those 4 sensors. And so the readout we're using in this example is the SuperDAC 1586A, and it has an advantage of being able to connect to the 7109A, and now you can run a program from the SuperDAC that will take data on the sensors and record the data, and we'll go through those steps. So in this case, also we are bringing in an external reference probe so that we can reduce the uncertainty if we need to by bringing in a lower uncertainty reference probe and measuring it with the SuperDAC. So here's a picture of the -P option, the process electronics option. And so we're showing this picture because the next step is to connect the transmitter to the 4 to 20 milliamp loop circuit, as shown here. It's identified with the number 5 there. There's also well, I guess in this, I call it the DUT input, but here it's called the RTD terminal. And you can also connect a reference thermometer to the 7109A to improve to switch over to an external thermometer that can either help reduce uniformity error or just have a better probe in general if needed. But in this case, the reference probe is connected to the 1586A. Then we go over to the 1586A, and we're going to configure the channels that we need. And so, in this case, we're going to have channels 1, 2, and 3 on the scanner configured. Once we have the channels configured, then we go to the automated test screen, and this is where we configure the test similarly like we already talked about in the 7109A. And this is just going through the menu of setting up the test. We're going to use control source. That way the 1586A will tell the 7109A to transition to the temperatures as needed, so you don't have to use any external software to do this. And let's see, this is where you are setting up the set points, the tolerance and stability and soak times or dwell times for each set point. And then you go ahead and hit start scan when you're ready to start running it. So we're also simultaneously going to be calibrating the 4 to 20 milliamp loop on the transmitter by using the 7109A. So we have to go into the 7109A and enable loop power to energize that circuit so that we can calibrate the transmitter. So we start the test, and then we start going through the different set points. And similarly, the 1586A will have a graph mode if you want to see the graph of the temperature as it's going. Here is the result from the first set point, where we have some statistics telling us what the standard deviation is, what the max and min average, and this is all recorded into a file that can be exported to a computer and further analyzed. And so that's the next step, actually, is after you finish taking all the points and recording the data, then it goes into a CSV file, and so it can be opened, and the data is all date and time stamped, so it can be saved and works out really nicely. So we've talked mostly about using the 7109A and 6109A for calibrating sanitary sensors or tri-clamp sensors. But in general, because of the tank size and the good uniformity specs, it's useful for many of the other common calibration applications that are in a cal lab or in a manufacturing and testing environment. So some of the other applications that we see customers using these for is thermocouple wire testing, sensor validation, because you can load up a lot of small sensors in this tank and validate the sensors. You can also use it for traditional characterization of temperature sensors like PRTs and thermistors. You can calibrate integrated thermometers like the Fluke stick thermometer, for example. In general, the tank is large enough to accommodate a lot of these explosion-proof type transmitter heads or other types of industrial temperature sensor heads. So with that, we have from our previous presentations of this webinar, we've had a few questions, so we thought it would be good to cover some of those, but we're happy to continue talking about these also in the Q&A portion of this webinar if you have more questions. But we get a lot of questions about what are the fluids that can be used with these baths, and we recommend the 200.10 silicone oil for the 7109A and 200.50 oil for the 6109A. These are the oils that we use in the factory and service centers to calibrate these baths. One of the complications with baths is if you change to a different fluid, then it possibly could change the specifications. And the engineers did test these baths with some different fluids just to make sure there was nothing strange that would happen or anything. But silicone oil is the most common, certainly for this temperature range. But other fluids could be used, like some of them are hard to get a hold of nowadays, like the what do they call it? Flora inert type fluids, alcohol, water, ethylene glycol, and they're not designed to work with salt, so we don't recommend putting salt in the 6109A. When working at freezing temperatures with set points below zero, so one of the challenges with tri-clamp sensors is these flanges and the connectors and whatnot are large enough that it can be really hard to keep a lid on top of the bath. If you are going to let the bath stay at a temperature below zero, it's best to keep a lid on it. You don't have to have a lid on it, but ice buildup will happen at a higher rate if you don't keep a lid on the bath. If I remember correctly, there are some lids with some holes machined into them to accommodate probes with longer sheath lengths that can go through the lid and into the fluid to help fight this type of issue. The specifications are applicable with the access cover or the lid removed, but there are some details in the spec table where, if I remember correctly, there are some small, in a couple of situations there may be an addition that has to be made without using the tank cover or the access cover. And these units are designed to be transported with the fluid left inside of them. But when you do that, just make sure that the transport cover is installed. It has a nice gasket on it to seal the tank access. And there's also an overflow port plug that has to be installed. It has an O-ring in it. It seals the tank right up. But then as you're using the unit though, make sure you remember to, especially if you're going to be warming up the fluid to higher temperatures, the fluid will expand. And if you forget to take the port plug out, then you might have a mess on your hands if the oil overflows. And the bath is designed to capture some of the overflow, but those of you who have used baths before are familiar with what can happen, what kind of a mess that can create. So those are just some tips that we wanted to put out there. So with that said, I think that pretty much finishes up the prepared portion of the webinar. So I'm going to turn the time back over to Nicole.
I'll take it from here. So that concludes the presentation portion, and now we're going to move to the Q&A session. So as a reminder, if you'd like to ask a question, send it through the question box in your webinar controls. It's on the right side, and I'll monitor those as they're coming in. Let me see if we have any. Okay. Let's get started. I think you answered the first one. What bath fluids can be used in the 6109 and and the 7109A baths? Let me go to the next one. What equipment does the 6109A and 7109A product line interface with?
Okay. These baths interface with the 1586A, and that reminds me, we've had some people ask if like the process calibrator that uses the HART communication protocol if they will work with this bath as in an automated system, and I don't think that feature is available yet. I'd have to check and see if that's a planned thing or what, but I know currently it's not available. So does that make sense? So these will interface with the 1586A readout, and it's automated, built-in program like we went through in the presentation, but it doesn't interface with other process automation products like a process calibrator.
Like the Fluke 754.
Yes. Yep.
Okay. How fast does temperature change? Are you with me? I think I lost you.
Nicole, something's happening with the audio. I'm not able to hear what you're saying.
Now?
But it could be on my end. I'm getting a message that the audio connection has been lost.
All right, Mike, you're going to have to sum it up then.
Okay, now I can hear you.
Okay, perfect. It might be I got a call that tried to come in. So the question was, how fast does temperature change?
That's a good question. If you don't mind, I'm going to go down to. What did I do here? I'm going to go down to the spec table. Let's see, where's it at? Oh, farther down. Okay, so typical heating time is examples here for going from 35 to 100, about 25 minutes. Going from 100 to 250, 45 minutes. Cooling time, so this is the heat only bath. Going from 250 to 100, 35 minutes, 100 to 35, 55 minutes. Typical settling time is about 15 minutes for the 6109A and 10 minutes for the 7109A. So sorry, I was just looking to see if there's any other information on the next slide. So that gives you a general idea of how quickly these will change from one temperature set point to the next. So
I don't see any more questions that have come in. So I want to remind everyone, if you have questions, you can reach out to me directly at nvanwert@transcat.com. Our phone number was listed on the last slide, and we will send follow-up slides later this week. So also you can visit us on the web at transcat.com. And I appreciate all of you joining us today, and we hope you got something out of the presentation. Thank you, Mike, for presenting. And I hope you continue to join us for future Transcat e-learning webinars. Thanks, everyone.
Thanks, Nicole.